This video will introduce you to our paper called A Prior of a Googol Gaussians, a tensor ring-induced prior for generative models. In this paper, we construct a flexible plug-and-play prior for generative models, such as variational autoencoders or generative adversarial networks. With a proposed prior distribution, we can train a conditional generation model on partially labeled data and sample from it, specifying only some properties. The key component of the proposed prior is a tensor ring decomposition that allows to store a discrete distribution with a small number of parameters. For example, to compute a value of p at position 0 to 1, we compute a trace of q10 times q22 times q31. Tensors q are learnable parameters of our model. This decomposition is formally defined as shown on the slide. Here, three-dimensional tensors q are called cores. In this decomposition, we can marginalize the distribution along any variable by summing the corresponding core along the first axis. We can also compute a normalizing constant efficiently by marginalizing out all variables. Since we can compute marginal distributions and a normalizing constant, we can also compute conditional distributions and sample with a chain rule. We generalize the tensor ring representation to continuous distributions. We train a mixture of Gaussians with an exponential number of components placed in nodes of a high-dimensional grid. We store components' weights in the tensor ring format. Learnable parameters are the means and the variances of one-dimensional distributions and cores of the tensor ring in pipe C. In such representation, we can still compute marginal and conditional distributions and sample efficiently. We call this family of distributions a tensor ring-induced priors, or TRIP for short. Moreover, the likelihood computation in the proposed framework is differentiable. Hence, the described distribution can be used as a replacement of standard Gaussian prior in variational autoencoders, generative adversarial networks, and other generative models. The experiments show that tensor ring-induced prior forms a more expressive latent space both in variational autoencoders and generative adversarial networks. We demonstrate an improved performance in Fréchet inception distance and evidence lower bound on Cypher and Celiba image datasets. TRIP allows us to solve the subset conditioning problem, a conditional generation with some unspecified properties, without a direct missing values imputation. We also derived an evidence lower bound for partially labeled datasets. Experiments show an improved result for subset conditioning problem, especially for high attribute missing rates. Thank you.